Okay. So looking at part 3, excuse me, we're continuing with what is called starting with what is called the differential rate law or rate expression. You will hear this and see this on an AP test a couple of different ways. They will either say differential rate law, or they will say differential rate expression, or they may leave the differential off and just say rate law or rate expression. It all means the same thing, okay? So if you see rate, then you automatically should know what you're talking about, okay? These are not difficult, I promise you. All right. The problem with reactions is this is something that we're going to get into with when we get into the next unit on equilibrium. But reactions are reversible. They go both ways. So at the same time, in a beaker, you've got a reaction going towards the products, and at the same time, you have the products going back towards the reactants. And it gets really messy. It's called forward reactions and reverse reactions. And when you're talking about the rate of the forward reaction equaling the rate of the reverse reaction, you are at equilibrium. Okay, and that's what we're going to get into next, but we're not there yet. So, to avoid that, we're going to discuss reactions soon after mixing. So basically, you're going to throw the chemicals together. What is it like right after mixing? We're not going to worry about when you get a buildup of product or any of that going on. So we're really looking at what's called initial reaction rate. You begin with pure reactants, you mix it, then you measure the speed of the reaction over time. How are you going to do that? In an experiment, go ahead, what?
Is it the rise over the rate?
Well, that is looking at part of it, yes. But in terms of in the experiment, while the reaction is happening, you're going to be either counting number of bubbles, which would be kind of hard to do because bubbles are a really good sign of a reaction. You're going to measure the mass of the precipitate, so how much stuff do you get falling to the bottom, what's solid. Or you're going to use something called spectroscopy to measure color change. That is what we're actually going to do in a lab when we get back from Thanksgiving on Wednesday after we get back. It's called the crystal violet reaction. So you're actually going to mix some chemicals together. They're going to turn a really pretty purple. You're going to put it in something called a spectroscope, and you are going, it's actually a colorimeter. You're going to measure the saturation of the color, and you're going to watch it as it changes over time. Because over time, as the reaction proceeds, that purple color is going to fade away. Once the reaction is completely done into equilibrium, it would actually be a clear solution. So the computer or your LabQuest is actually going to measure all that for you. But that is what we're doing when we get back from Thanksgiving. We're going to, like I said, we're going to be talking about initial reaction rates throughout our whole thing. So rate equals a K, which is a constant, times the concentration of whatever chemical you're dealing with raised to some power. So you're going to deal with an exponent, and we're fixing to talk about how you figure out what that exponent is. But if you notice, this K is not a big K, it's a baby K. Okay? And that is important because a big K deals with equilibrium. A baby K deals with rates. So on AP tests, you have to be sure that they can tell whether it's a baby K or a big K, because they will count it wrong if you do it the wrong way. So be sure you have a little K versus a big K. And I know there's not a lot of difference except for a baby K has a taller little line at the beginning. Okay, so be sure that it looks like that. Another way to look at it is what we talked about before about the change in concentration over the change in time. That's your slope, rise over run. Okay. We're going to be analyzing concentration. And remember, concentration is capital M for molarity. And rate. So if you are looking at any problem and it gives you concentration and it talks about rate, then you know you're dealing with a rate law expression. And that allows us to figure this out. And remember that this, the rate, what you're really talking about is change in molarity over change in time. Because it's concentration, the change in concentration of the change in time. So it's really change in molarity over change in time. All right, so rates generally depend on reactant concentrations. To find the exact relation between rate and concentration, you have to conduct experiments. It does not just come out of thin air. Either they are going to give you data from an experiment, or you're actually going to conduct an experiment yourself. And you're going to collect the data and then interpret it. So if we have this general equation here for this reaction, A plus B gives us some product X. Well, if you see the C that's over the arrow, sometimes over an arrow you'll have just a delta sign. And delta sign just means that that's heat. Okay, so heat being added to a reaction, that you will see sometimes. But if you see an arrow and above it is the letter C, that means anything else. And that anything else is a catalyst usually. And that catalyst is important. And if they give you the concentration of the catalyst, it's something you're actually going to have to put into the rate expression, all right? So you will always have this. Your initial reaction rate is going to equal K times whatever concentration of A is, raised to some power, we don't know, times your concentration of B, raised to some power that we don't know, times your concentration of C, which would be your catalyst, raised to some power. Don't always have a catalyst, but if it is there, know that you're going to use it in your rate expression. And also, in very little letters underneath that, it says, note the catalyst is included only if it is homogeneous, which means it's in the same phase of matter as the reactants. So if your catalyst is a solid, and your reactants are actually gases, then you won't deal with the catalyst. But if they are all gas, then you would have to include it. Okay, so it has to be homogeneous. All right, so looking at what all of these mean, K is your rate constant. Your concentrations, the molar concentration of reactants, remember that is going to be your molarity, which, remember, molarity is actually just moles per liter of solution. Okay? And then this M, N, and P, those are your numbers that are your exponents. So those exponents stand for the order of reaction for whatever that is. All right, so that is lingo that you need to know. The exponent, you're going to call it order. It's going to either be a zero order, or a first order, or a second order, or a third order. Can be fractions, but usually not. Usually they're whole numbers. Okay? And you're going to determine that from some experimental data. All right, so looking at this rate constant K, that little baby K, K is definitely temperature dependent and must be evaluated by an experiment. Y'all don't have that? Yeah, okay. If you're looking at this, at your equation, rate equals baby K times the concentration of some reactant or product, we're just going to call it A, it's going to be raised to some power. We don't know what that is yet. But that power, that exponent, is really going to affect the whole reaction. Okay, it's going to tell you how fast the rate is going to be, how fast the reaction is occurring. In terms of looking at units, be careful about the unit. Okay, and we're going to talk about the units more as we go along. But the rate is typically molarity over time. That's the unit for it. Your concentration is also molarity. And then usually your K is going to be over some time, whatever time is. Okay? And we're gonna talk about that. Don't worry about the units too much at the moment, but the units are important and they will count off if you do not put the correct units. So I'm going to show you how you figure that out. All right, skip on orders. The order with respect to a certain reactant is the lingo you need to use. If they ask what is the order for reactant whatever, then you would have to say the order of it is first order with respect to A, or it is first order with respect to B. So they're going to expect you to write out a sentence. Don't just say first order. First order for what? Which one is first order? Is it reactant A, reactant B, or is it product C? What is it? You have to be sure and be very specific. But that order is the exponent on the concentration of whatever thing you're looking at. The overall order is simply the sum of all the exponents in the reaction. So here, as an example of it, okay, well, if you have the rate is equal to K times our concentration at A, and let's say it's raised to the first power, times concentration of B, raised to the second power, times the concentration of C, raised to the third power. Well, you would say the reaction is first order with respect to A. The reaction is second order with respect to B. The reaction is third order with respect to C. Okay, do y'all see where I got that? I'm just looking at the exponent and I'm saying, okay, if the exponent is 2, that means it's second order. If the exponent is 3, that means it's third order. If we are asked, what is the overall order? You would say, what? It's the sum of the exponents. What is the sum of those exponents? 6. So you would say the overall order, it is 6. The overall order is 6. Is basically all you have to say. Okay, so if it asks for overall order, all you got to do is add the exponents together. It's easy, y'all. It's not, this part, I promise, is not hard. All right, now in terms of what these mean, if it is 0 order, The change in concentration has no effect on the rate. So concentration of the reactant has no effect on the rate. So you would have rate equals K times your concentration of A, and it would be raised to the 0 power. What is anything raised to the 0 power? 1. All right, so anything raised to 0 is 1, so that means it is just rate equals K. Because if the concentration is 1, K times 1 is just K, so rate equals K. Makes it an easy equation. If it is first order, it is directly proportional to the reactant concentration, which means if you double the reactant, the rate doubles. If you triple it, the rate triples. So, as an example, if we have rate equals K, concentration at A to the first power. Well, let's say that your concentration of A, let's say it is 2. We double our concentration. It goes from 1 to 2. We double it. Well, if it is 2, if it doubled, what is that going to do to my rate? It doubles. So it would be 2 rates. If I tripled this concentration, I changed the concentration to 3, what would that do to my rate? It would triple it. Okay? So if it is a direct relationship, a direct proportion, then it's first order. Second order, the rate is quadrupled when the reactant is doubled. And it increases by a factor of 9 when it's tripled. So for this one, all right, you have rate equals K, and let's say we have our power of 2, or our concentration of 2. Well, if we double that, it's second order, so it's got a 2 there for an exponent. If our concentration is 2, that's suddenly 4, right? So we would have 4 rates. What if our concentration was tripled? It would be 9. Does that make sense? Okay. So if you see in the when you're comparing and you see this, that if this concentration doubles, then the rate goes up by 4, or if it triples and the rate goes up by 9, then you would know that it is second order. Fractional orders are really rare. Third order is really rare. Really, you're going to see 0, first, and second order most of the time. And really, most of the time, it's going to be first and second. All right, so this, you can read through this. This is exactly what I was talking about. So if you're looking at this, you're going to, depending on what that exponent is, you're going to say, if the exponent here is 0, I'm going to say the reaction is 0 order with respect to A. All right, so you can just kind of look through that. Now, actual examples of what that means. Look at this table. All right, this is something that is called table logic. You can either work out the math, or you can just look at the table of data and look at the pattern and know what it is. Table logic is a lot easier and a lot faster. I will show you the math later if you are just determined to